Welcome to Deep Learning Talks. So today's topic that we want to talk about is continual learning, and we have seen learning get resonated with a lot of other words, right? Right. So we have seen deep learning, right, and we have seen traditional learning, which is the training part. Then we have heard about representational learning. We have also heard about reinforcement learning. But what the hell is continual learning? uh, I was listening to Demis Hazzabis and I was reading about what DeepMind's strategy is, uh, you know to conquer AGI. So he mentioned one critical topic. He said, before we reach AGI, there's one area that I'm expecting a breakthrough in. Right? There are multiple areas, but this is one of the areas. One area, one breakthrough has to happen in this area, which is known as continual learning. Right? So before we understand continual learning, I want us to understand what exactly is the traditional deep learning. Right? So whenever we talk about deep learning, we resonate it with the deep neural networks, the study of deep neural networks across different modalities. Sometimes we are dealing with images, sometimes we are dealing with sequences, time series, and then multimodality, right, or multimodal data. So deep learning is all about those hierarchical neural networks, the neurons that we stack vertically and horizontally. And we built traditional neural networks, and sometimes we add convolution blocks prior to the linear layer. Sometimes we add multiple encoder decoder stacks. So, and we call them different variations of deep neural networks. And the whole area, the whole study of these particular deep neural networks is nothing but deep learning, right? Now, what really happens in case of a deep neural network? Consider or assume deep neural network as a simple model, right? The model undergoes a training phase. There is one particular phase which is very explosive, very time intensive, very compute intensive, which is known as the training phase, where the model tries to learn. What does the model tries to learn? Model tries to learn the data, right? Model tries to learn the representation, the features in the underlying data. And then model produces some weights, and the weights are learned and the weights are saved, right? Then what happens is we freeze the model, right? Freeze in the sense, then when we stop learning, right? Let's say the model the model has undergone n iterations. After n iterations, we say that the loss has been minimized. We have reached the global minima on the U curve. And we applied gradient descent. The model did its forward pass and backward pass, and then in this whole process of training, we minimize the loss. Now we have some model weights. Those model weights are now frozen in the sense, we don't retrain the model again and again. Again and again means every day, right? Now the model will be deployed so that people can query the model. So this phase is known as inference phase, querying phase, where we will call the dot predict function of the model. The dot predict function will compute the forward pass, right? The dot predict function already has the model weights, and whenever I want to query something, let's say if I'm doing X token prediction, I will give it some text. It will call the predict function and it will predict the next particular word. This is the inference phase or predict phase. Then there was training phase. Training phase is very compute intensive, right? Inference phase is also compute intensive, but with respect to QPS, the model can have very high QPS, right? uh, QPS means queries per second. A lot of users can throw concurrent queries per second on your deployed model, right? So in all of this, in all of these phases, or between the training phase and between the inference phase, the model weights do not change. After training, we freeze the model weights, right? Now, what really happens? This is traditional deep learning. Now, what really happens in case of humans? In case of humans, the concept of freezing the weights is not true, right? So humans continuously learn while operating in the world, right, like an agent. So the fundamental intuition of a biological brain is, it does not freeze my model weights, it does not freeze my neurons, my biological neurons. Every day, every second, I'm able to interpret new things, feed in new things, forget older things, and mutate and evolve, right? That's how the biological brain evolves. So this is like real intelligence. Are we simulating real intelligence? No. We are just trying to learn the representation of some stored data. Those stored data produce stored model weights or model parameters. Then those model parameters are further used to query, right? So the classical deep learning or the traditional deep learning training is not continuous learning, right? In the standard training, we are minimizing the loss function, right? We optimize the loss using gradient descent. right? We freeze the weights. We use dot predict at inference. That's it, right? But why do we freeze the weights? I mean, if I were to ask, why do we freeze the weight? Because we cannot afford to keep on updating the weights at every minute, every second, or every day. Why? Because there are billions of weights, there are billions of parameters. Parameters and weights are used interchangeably, right? There are billions and in today's large foundational models, we have trillions of parameters, trillions of weights. How can we afford to continuously update the weights every day, every second, right? We cannot. It's not possible to do online streaming and online training or live training or continual training every second, right? I might also end up corrupting the previous knowledge. I might have to update all the weights, right? So it's not pretty straightforward. That's why we freeze the weights. Freezing the weights is straightforward, right? But now what does continual learning say? Continual learning says that what if I could continually learn lifelong from my environment, right? Across multiple tasks. I perform task A, right? And then I learn something, and I perform task B after task A, then I learn something else, right? But what really happens in those? I mean, what are the challenges? So there are multiple challenges that can happen in case of continual learning, right? So continual learning basically means here that instead of traditional learning, or after the traditional learning is over, I am getting to perform task A, I will learn something from that. I am getting to perform task B, I will learn something from that, and task C and task D. As I move or in order in time, in the time dimension, I will keep on learning new things. I will keep on accumulating my new knowledge, right? I will not freeze my weights permanently, right? But in case of ChatGPT, when the first version was launched, we could always see that it was trained on a particular date, and after that its weights were frozen. And all the time when we used to query ChatGPT in 2022 maybe, then it used to tell us that I only remembered information till particular date, when my weights were frozen. Today it does not tell, because it has the capabilities to browse the web, and it has the capabilities of memory. It operates like a RAG. So today the things are different. But previous large language models used to give a disclaimer that I don't know who your president of today might be, because let's say today is 2024, but I was last trained in 2022, something like that, right? So we have to periodically train these models, cyclically train these models. Let's say we train them biannually, right? uh, Once or twice in an year, or once in a year, right? Something like that. So this is basically a human learning model. We keep on evolving from our experience, from our actions. What do we do to make this particular thing possible, which is continual learning, right? So there are multiple things that can be done to make continual learning possible. But let's first see what are the challenges in case of continual learning. So one of the challenges that generally happens is catastrophic forgetting. Now what exactly is this? So since we are learning the tasks, or the from the feedbacks from the tasks in a sequence, what really happens is, once we try to learn task B, the neural networks overwrites the useful weights that were needed for task A, right? So new learning kinds of overrides the old learning in the previous sequence, right? Previous task performance degrades significantly. This is what happens. This is what basically is meant by catastrophic forgetting. Now, in what is stability plasticity dilemma, right? So this is also a very famous very famous word, that stability plasticity dilemma. So what really happens is, uh, I mean, here plus too plastic means we are forgetting the old knowledge, and too stable means we cannot learn the new knowledge, right? So if we have high plasticity, which is too much plastic, then we tend to forget the older knowledge. We don't learn fast. Forgetting is more common. Whereas if we are too stable, we cannot retain or remember the new knowledge. The learning gets slow, right? So we need a good trade-off between plasticity and stability, right? So these are some of the challenges that we generally see in case of continual learning. But now, what are the techniques that we generally we use as engineers to simulate something like continual learning? So one of them is EWC, which is elastic weight consolidation. So what really happens in this particular technique is, we estimate which weights are really important for previous task, right? And penalize changing them so that they don't completely change. But this also does not scale really well, with a lot of tasks, right? So the main idea is that we don't have to change a lot of important weights too much, right? So this technique was known as elastic weight consolidation. Now we have one more technique, which is replay based methods, right? So which is also known as memory replay. So the idea here is that we retrain on old data while learning new data, right? So it's like we might have two versions. One is we're storing a lot of old samples with a memory buffer, and second is we are using a generative model to recreate the past data, right? This might mimic how humans rehearse and rehearse memories. So but the problem is that we have memory which is very expensive, right? Memory and compute, definitely both of them are very expensive. So this has its own challenges. Now the third architecture or the third idea is that why don't we mutate the architecture? Why don't we do something on the architecture? We have tried playing around with the weights, we have tried playing around with the memory. Now what about if we play around with the architecture? So the idea is add new neurons, or maybe new sub neural networks for newer tasks. As we see newer tasks in the sequence, why don't we add new neurons and new subnetworks in the architecture? So it's like we progressively mutate the neural network, right? But here also the main challenge is that the model will have a dynamic architecture. The model will keep on growing, the model complexity and the model size will be a function of time. As we grow with time, the model size and model complexity will keep on growing, right? So this is also a key challenge. So what about the large foundational models? What do these kind of models do today to simulate continual learning, right? So since we have a lot of challenges, so what do the GPT family and the Claude family, what do they do? So they do not continually update the weights per user interaction, per time, per day, right? They don't do it every day, right? Or with every user interactions. What they use is a hack, which is basically known as retrieval augmented generation, right? So there is a concept of frozen model, the weights, right? The parameters. Then there is a concept of memory, right? So, or knowledge base, right? So what they do is, instead of changing the weights per user interaction, they store new information in a database, which we very commonly call as a vector database. Then they retrieve the relevant information at inference time, at query time, not during training time, and then they inject that particular information into the context window. So the model might appear or behave as if it has learned, but the weights always stay frozen, right? So this is basically how we are trying to have a new paradigm. One paradigm to look at the model was only through parameters. The other paradigm is, why don't we look at the model with the way where we have a parameter which are frozen, which is its brain, and then we have memory. So we have decoupled the brain from its memory. There is one component which is known as the memory. There is one component which is known as the parametric weights. So when we combine both of them, we might call this model as something like a RAG, which is a retrieval augmented generation, right? So what is the paradigm shift here? Paradigm shift here is, we are looking at the parametric memory and non-parametric memory. The parametric memory here correlates or corresponds to the weights of the model. So all the knowledge that we have learned from the internet, right, is the weights of the model. That is our parametric memory. So all the knowledge that we are trying to store now from external specific knowledge is basically our memory. So the modern AI systems kind of use this particular paradigm to simulate as if they are constantly learning, right? So what about the idea, we heard about a term known as online learning. Does it even exist? So there is a concept of online learning. This is not continual learning, but this is very similar to that. But here, online, in case of online learning, we are continuously updating our weights on the streaming data. This is also used in certain systems like recommendation systems and ad systems. But here usually the learning rates are very small. The architecture is very small. The we do some sort of periodic batching. We don't online learn at every particular nanosecond, right? But large foundational models cannot do online updates, and that too real time streaming updates. That is highly unlikely, right? So we know that why it has not been fully solved. First thing is, it's very very expensive. Why it's very expensive? Because we cannot mutate all the weights all the time at every user interaction every day, right? And there are challenges like catastrophic forgetting that we saw. There are challenges around stability and plasticity. Then there are challenges around memory. So we do feel that memory and compute, both of these things in this particular case, is very expensive, right? So what are the most promising areas where we see ourselves moving? So one area is obviously RAG, which is kind of a hack. Then another area is there are multiple parameter efficient fine tuning techniques, which is one of them is LoRa, LORA. Then uh, we have something which is, why don't we explore as a research area the idea of meta learning, which is we question from the first principle, how to learn, how our models should learn. So this is one of the ideas that we are exploring, and we might change the way that we have been learning. Parameter efficient fine tuning obviously is one of the areas. Then world models, right? So why don't we change the latent representations continuously, and why don't we produce latent representation in such a way that we understand the physical and spatial structure also, so along with text, right? So there are some research that is going on in this particular area, and the meta ideas that surround this particular area to solve it, right? So uh, I think this particular area is where the most amount of challenges lie. If we are able to have a breakthrough in case of continual learning in this particular area, then that would be one step closer to having a super intelligence, having artificial general intelligence system. Okay, I think that's good for this particular video. I will see you in the future videos. Cheers. Thank you.